Welcome back to some more Calculus 2 practice problems, and today we're focusing on differential equations. So what is a differential equation? A differential equation is just any equation that has a derivative in it, like this one. This right here is a differential equation. It says that 3y prime plus 5y will equal negative e to the negative 2x. And in the differential equations class that you might have in your college, you're going to be able to find these functions. But in calculus, we're not concerned about finding the functions, we're more concerned about verifying that they are the general solution, right? So in order to prove that this is the general solution, let's just plug in y and y prime. So in order to find y prime, let's just find the derivative of this function. The derivative of this function, let's see, a negative 2 e to the negative 2x from the chain rule. And let's plug in. We have 3 times negative 2e to the negative 2x plus 5 times the original function, e to the negative 2x. Does this equal negative e to the negative 2x? In other words, is this the correct general solution to the differential equation? Well, let's see. We have a negative 6e to the negative 2x plus 5e to the negative 2x. And I'd say that that does simplify to negative e to the negative 2x. So yes, this is a solution to this differential equation. So yes, it was a solution. How about this one? Y equals cosine x, y double prime plus y is equal to 0. Well, what is y prime? Y prime of cosine x is negative sine x. Y double prime is a negative cosine x. So does negative cosine x plus cosine x equal 0? Yes. So this is a solution to this differential equation, right? Now they ask us to verify the general solution again, but also find the particular solution. So the particular solution means that we're going to be able to find what these constants are, given these initial conditions they're called. So let's look at, we're going to need y double prime and y prime from y, right? So what is y prime? Well, the derivative of that c1 is just 0. It's just a constant. The derivative of c2 ln x is c2 over x. Y double prime is going to become negative c2 over x squared. And you can check that, but let's plug it in now. Is x times y double prime negative c2 over x squared plus y prime c2 over x equal to 0? Well, let's see, the x will cancel the x squared. We have a negative c2 over x plus c2 over x equaling 0. So yes, this is the correct general solution. How are we going to find the particular solution? Well, y prime is equal to 1/2 when x equals 2. That this initial condition is going to allow us to solve for c2. They say that y prime, we know that y prime is equal to c2 over x. They say that it's equal to 1/2 when x equals 2. So plug in x equals 2, we have c2 over 2. So you can see that c2 is just 1, right? c2 equals 1. They also tell us that y equals 0 when x equals 2. The original function y, see, y is equal to c1 plus c2 ln x. But we know what c2 is now. It's just 1, right? So it's c1 plus ln x. It's equal to 0 when x equals 2. So y is equal to c1 plus ln 2. And that's equal to 0. Does that tell you what c1 is? Yes, c1, you just subtract the ln2 from both sides. So c1 is equal to negative ln2. Finally, we could rewrite y as c1 plus c2 ln x. So this would be the particular solution. It is not only a general solution that satisfies this differential equation, but it also satisfies these two initial conditions. So this is called a particular solution. Okay, now let's look at something called a separable differential equation, right? And did I spell separable wrong? I think so. Separable. Diffeqs, or differential equations. Find y. We can find y from this differential equation. Really, this dx or dy over dx is a y prime, right? So it's something we're used to seeing. Except we can move or work backwards using integration to find y, right? So, like in the previous example, imagine they gave us this right here, and they said work backwards to find y. Well, we could integrate it and get this, and when we integrate this, we're going to get a C1 from that last integration, right? So let's look at now this separable equation. How do we solve these? The general strategy is that you can rewrite y prime as dy dx and multiply both sides by dx. And now you can see that we have dy equals this equation. And if these two are really equal to each other, right, they're equal to each other because of this equal sign, we can just integrate both sides and it wouldn't change the value of the equation. So the integral of dy is y. There's how we found y, right? What is the integral of the right side? Well, we could do a u sub. We could call u equal to the denominator. Du is then e to the x dx. That's good. That's what we have on top. So it's the integral of du over u, which we know turns into natural log of the absolute value of u plus some c, right? Which means that our answer is going to be natural log the absolute value of 4 plus e to the x plus c, right? And if we wanted to figure out what that c was, we could get some initial conditions and figure it out. But this is just the general solution. This is the general solution because we have a plus c in there. Let's look at another one. dy over dx equals tangent squared x. So we can follow the same steps and get that y equals the integral of tangent squared x dx. So I did a video on these trigonometric integrals, and after watching that, you should be able to figure out that we could separate this into a secant squared x minus 1 and integrate them separately. The integral of secant squared x is tangent x, and the integral of negative 1 with respect to x is negative x, and we have a plus c. So given this y prime, we're able to find y, right? That's really just integration. But this is an example of a basic differential equation that we can separate to find the general solution. So that is pretty much scratching the surface of differential equations in calculus, calculus-based differential equations, doing the derivatives and integrals. In the beginning videos of this series, we looked at a lot of applications of differential equations and particular solutions. And we can go a little bit further now and look at growth and decay, right? If a city's population starts at 5,000 people, 1 year later it's 6,000, find the population after another year, given the rate of change of the population is proportional to the population. So this sentence right here is key. We're going to be able to set up a differential equation. The rate of change of the population, given that it is with respect to time, is proportional by some constant of proportionality k to the population. This is a differential equation that now we can solve by multiplying both sides by dt. And we want to get all the p's to one side, so let's divide this p down here as well. And the dt's will cancel. Now we have dp over p equals k dt. We can integrate both sides and get a p, or ln of p, equals kt plus c, where this c is the combined sum of the constants from both integrals. We looked at that too in the beginning of this series. But we don't want ln of p, we want p. So let's just raise both sides by e to get that p is equal to e to the kt plus c. We could also simplify it a bit further, because this, when you're adding in the exponent, you could really write it as e to the kt times e to the c, right? You could move backwards and combine those to just one base of e. But the reason we're moving backwards now is because we could write e to the c. That's just another constant, right? E to the c is another constant. So we could just write this as that new constant e to the kt. This look familiar to you? Maybe in college algebra or an intro to finance class or a liberal arts math class before. You might have seen PERT, where P is the principal value, R is the like rate of your investments maybe, T is the time in years, and E is obviously the exponential function. So this is how that exponential function was created using calculus, and now we can use it here. We only have to figure out what C, E, or C and K are, right? So we can use this first sentence to figure out what C is. In this case, C is like the initial population. So we start with this, P equals C e to the kt. At t equals 0, P equals 5,000, right? At the start, times 0, the initial population is 5,000. So you can plug in t equals 0, you get 5,000 equals C e to the 0, e to the 0 is 1. That tells us that C equals 5,000, which you already knew because C is like the principal value, right? So now we have P equals 5,000 e to the kt. You also have to figure out what k is to have the finished equation. So what is k? Well, they tell us that 1 year later, the population is 6,000. So that means 6,000 equals 5,000 e to the k, right? Because t is 1. So can we figure out what k is? Yes, we could divide both sides by 5,000. So on the left side, we're going to get 6/5. That's equal to e to the k. Can we figure out what ln, or what k is? Yes, by taking the natural log of both sides. So what happens on the right side? What is the natural log of e to the k? Well, we can bring the k out front, and we're just left with k times natural log base e. Natural log base e of e is all just 1, right? When you have a base and a log of that base, we just get 1. So this whole right side just simplifies to k. We have k equals ln of 6/5, right? And that is the exact value of k. So let's plug that back into our formula. We have P equals C, which is 5,000, e to the k times t. And they want us to figure out the population after another year. So this part really isn't calculus, right? We did this in many classes ago. But the differential equation part is where the calculus comes in. So let's plug in. You can see that after another year, we're now at year 2, which means t equals 2. So when t equals 2, what is p? So let's see, p equals 5,000 e to the ln 6/5 times 2. And you can plug that into a calculator. 5,000 e to the 2 times ln of 6/5. You're going to get 7,200. Is that consistent with our answers? Like, it wouldn't make sense if we got an answer below 6,000 or below 6,000 or 5,000, right? Because it's obviously growing. This is exponential growth, right? So yes, this answer is reasonable and it is the correct answer. Let's look at the other application of diffie-Q's, decay. We typically look at half-life a lot with this, right? Let's take some carbon-14, what do you call it, isotope, is that what it's called? Say the half-life of this carbon-14 is about 5,730 years. So after 2,000 years, what percentage will remain? So we already derived the equation that P equals CE to the KT, right? But they gave us like a lack of information here, right? at least in the other problem, they gave us a few initial conditions. Well, this is going to be all that we need. So what amount will remain after 2,000 years? But it says any given amount. Here's how we can find out what k is. We can use this first sentence right here to figure out what k is. We know that half the initial amount, so we don't need to even know the initial amount. We just know that half of it, half of c, will occur when t is 5,730, right? It doesn't even matter what c is. We just know that half of c will be present after 5,730 years. The reason why it doesn't matter what c is because they cancel each other in the equation. So we can just use that to solve for k. We're no longer concerned about finding c, right? So it looks like we can ln both sides, right? So then we have ln of 1/2 is equal to k times 5730 times ln of e, and that ln of e is going to go away because it's just 1, and we can divide both sides by 5730 to get k. K is just ln of 1/2 over 5730, and this is general. For any kind of half-life problem, the k value is always going to be ln of 1/2 over the half-life. So let's rebuild our equation. We have P equals CE. K was 1 over 5730 times ln of 1/2, right? And then we also have T. So notice that they gave us 2,000 years for T, and they want us to find P, or what percentage of P will remain. So let's see. We're going to, the percentage part is just going to come from here. We're not really concerned about C, right? Because whatever this is, like for example, if this all became 0.5, then P would just be 0.5 of C. So when we're talking about percentage, we're just caring about this right here, this E to the 1 over 5730 ln of 1/2, and we're multiplying that now times 2,000 years. When you plug that into a calculator, let's see what we get. We have E to the 2,000 divided by 5730 all times ln of 2. And the answer we get is 0.785 about, right? So what that means is that P equals C times 0.785. C is the initial percentage, right? Which means that P is going to be about 78.5% of that initial value, right? And this makes sense because if it takes 57 or 5,730 years to decrease by 50%, obviously if we're only at about 2,000 years, we're not going to be anywhere close to 50%. We're still 78.5% of this given amount is present after 2,000 years. So these are, like, we're scratching the surface in DiffyQ. You're going to look at a lot more growth and decay applications, and also look at like circuits and how those are related by DiffyQs as well. But for the calculus 2 part, this should cover about what you learn in differential equations.